Welcome to a rebuild video. I'm going to reuse this super nice case for something completely new and completely different. Since this case is in a super mint condition and it's free, and this product is absolutely useless to me the way that it is anyway, because I'm not working with nickel cadmium or nickel metal hydride or lead acid cells, so I really don't need this, and whatever this can do is something I could easily handle with anything else that I got a lot of other equipment that can do this anyway, so yeah, I don't need this product the way that it is, but I really need the case. So, and there is a super nice cooler with fan and the heatsink with you know, the way that the transistors are mounted and everything here. So yeah, it's already explained in a previous released video, and I will put the link in this video so you can find the previous video that explains all about this unit. But now I'm going to reuse it for something else, and then I will release a little video about this rebuild. So it's actually quite easy. Just poke the whole box to pieces, and what I want is to cut all the profiles to a much smaller size, so it's going to be a much nicer case size. I really don't need this big transformator. All I need is this one. A tiny little area around this is actually all I need. And I will take the front and the rear plate, and I will save these because I need the measurements for the height. And of course I need to save the bottom plate a little bit more, because here I got all the measurements for the screws and stuff, and where is the heatsink mounted and all that. I don't think I want this kind of mounting here for the bananas, and I only need 2 bananas. We'll see about that. And here I need to remember the 2 plastic spacers and a tiny little transparent spacer under the PCB is how this is mounted. Alrighty then. I cut the sides a lot shorter and made a new bottom PCB so I can mount the heatsink. At the beginning I'm just using the original bottom or the rear plate to simulate what I want to do. Here I made a little drawing. This is the mains, and I'm reusing a hole up here for on-off switch. I don't know exactly where I want my Arduino to stick out or my transformators to be located yet. That's what I'm playing with right now. I'm adding a little bit of isolation here, so I made this a lot bigger compared to the mounting area here of the heatsink. And the original PCB had some holes for the cooling, and yeah, actually all the holes here and the measurements, all that kind of stuff, I just stole from the original PCB and copied to this PCB. And now I'm playing a little bit with, maybe the Arduino is gonna be like this, but I want to access this screw so I can loosen the nuts and slide this out if I want to service something. And maybe it's supposed to go like this, and I think maybe the tiny little transformator like this or something like this tiny little size should be enough, because I only need about 2 watts to drive this fan, and half a watt or something like that to drive the display. So that's kind of all I need, right? So let's play a little bit with the fan. It's starting up already at 3 volts and just barely turning. So this is a 5 volt minimum voltage. I was expecting to add a little temperature controller on the heatsink with just an NTC and something that will just crank up the voltage on the fan so it's not annoying Listen to this. So this is 5 volts. So if I have this as my minimum speed, I'll be happy, right? So 5 volts, 63 milliamps. And this is 12 volts, 160, 170 milliamps. And I'm telling you, this sounds like a vacuum cleaner or something like that. It's like a lot of air coming out of this thing. So I bet this can cool quite a lot of watts. Wow, that is amazing. And it's getting ice cold. Wow, great. So here's the display that I made for this unit. Just a normal Arduino TFT and an Arduino Uno. Let's see. So my idea is it's going to show voltage, milliamps and watts. And at the moment I'm just simulating the inputs like this. And like that, right? So then I can crank up the voltage or the current, and then I'll get a really good resolution for everything with an Arduino. So this is a 0.1% resolution in the readout. I think that is absolutely perfect. This is definitely what I want. So all I need to know is how much power is this using, so I can find a tiny little transformator to power my entire circuit. I found a better transformator, rectifier, Schottky diodes. So I got about 12 volts, a little bit under 12 volts for the fan. And then I can regulate this to drive the Arduino. So that is fine. I'm trying to isolate my PCB here, where I want to add my regulation components, so it's not chassis mounted, but I want the transformator and the heatsink and the chassis to be connected to earth for safety reasons. And I've been playing a little bit more with the rear panel. I think this is a PVC, so it's really good to work with. I did some measurements here and all that stuff, but I'm so lazy I didn't want to cut all the holes and do a lot of stuff, manual work, you know how it is. So here's what I did. I made my own rear plate in 3D print. And just designed this in Fusion. It takes only a few minutes, it's quite simple. And then this slides in, and I got a rear plate. I didn't do this right, because when I was looking at this, I didn't see the sides is actually supposed to go all the way out to the end like this, and then it's actually supported all the way around as well, not only by this groove here in the top and in the bottom, but also at the sides. And if you look at the other side panel, I don't know if you can see this, but I didn't note this little detail here. So this is where the front and rear plates actually go in here. So now I need to 3D print a new one because of course I made it thicker so it's more stable, but now I can't put the sides on, and I'm not going to muck around with this and make this nice and beautiful. It's easier just to redesign it and print a new one. On the front also I made a new front like this. Of course I printed both of them before I tested one of them. So that is another little trick. That is a little bit stupid. I don't recommend you do that. I printed this in the PEGD, so it's handling quite a lot of temperatures. I made some holes here for the display. And here is my little display holder. I'm going to sand this and paint it, so it doesn't matter, it looks like this. See, it is not symmetric, the hole here where the display goes, so it goes that way. See? So when this one is mounted here, from the front it looks more or less like it is in the middle. I think this one is a little bit wider, but it's because I want to have this little edge here going here, right? So this one fits in that hole. I couldn't make this in one piece because then I can't 3D print it, because it needs to go flat this way, because I wanted this edge or to make it more thick. So yeah, when working with 3D print, it's a little bit challenge to figure this kind of stuff out. Oh, also this is the first design, and if you see here, I'm not really happy about the location or the placement of the banana connectors, so they are now moved up, so it's symmetric as well. And yeah, hopefully it's gonna look a lot better in a few hours. So while I'm waiting for the 3D prints, I might as well just play a little with the IGBTs I want to use. See, this size is a little bit too big, I guess, but this is a more normal size, and those are actually 1200 volts, and those are only 1k volts. So I'm gonna go with this type here. They're called IR64PH20K, so that should be 1200 volts, 5 amps. And I got quite a lot of them, and so I wanted to see if there's a difference in the gate emitter threshold. So here's what I do. I try and put this on my power supply, connect the gate with the collector like this, and just limit the power supply like this. Let's see what happens. So this is 7 volts, 120 milliamps. Okay, fine. Then I note this and then try some more. Okay, so that was quite easy. It was really fast to find 7.1. Okay, so those are the ones I will use, and there's a little bit of some over here anyway. The thing is that I want to be able to give each IGBT like a quarter of an amp, right? And at that current, the gate emitter is 7 point something, or this, and this is actually also the drive voltage, and I also want some volts in the feedback. So that means if I add like a volt of feedback to equalize the current, and then yeah, I think I'll be able to go all the way down to 10 volts. So from 10 volts to 1 kilovolt, and yeah, that is absolutely fantastic. Definitely what I want, because this load is not intended to go down to 0 volts. If I want to go to low voltage and high currents, let's just take some ready-made loads, right? So before I continue mounting any more of the IGBTs, I need to try if my isolation is actually working. So here's my good old maker. This is doing about 1200 volts open circuit voltage. I connected all 3 pins together, and now I'm testing this versus the metal. Oh, let me show you guys. It's supposed to look like this. Nothing, right? But ooh, this is not good. Damn it. There's absolutely no isolation. See? What kind of crap is this? So let's try this with a normal ohm meter at only a few volts. Look at that. Some kilo ohms, really? I am really disappointed. So let me see. I was actually starting to mount some more IGBTs. Is this a general problem that I'm having? I really thought I was doing everything correct. Okay, so those two are good. Now I'll solder these together and test test them with a Emitter as well. This is getting real interesting. Soldered all 3 pins together. Okay. No connection on low voltage mode. So let's try high voltage. Okay. No problem. Haha. Brilliant. No problem. So let me try and reverse the voltage. Nothing. And we're good. All right, great. So it was just one that was wrong. So this just proves how important it is to test what you're doing. Obviously, I'm going to crank this. I got another one that will do 2000 volts. So, because I only want to use them for 1000, but I actually want to test it double the working voltage for safety isolation. So this is the rear side. I didn't do anything. This is just how bad it looks. My bed is just that punked up. And so now we got this hole for my USB. Oh yeah. So to hold the USB connector, I just removed this from the Arduino. Press this in and bend the 2 flip flaps there, and then they kind of lock. And now I'm done. Thread here, and then this sticks into the hole, and then I can just put in 2 screws, and then I'm done. I think it's better to have the Arduino at the front instead of at the back, because there's a lot of wires for the display. So this is why it needs to be like that. If I put back the rear plate here, oops, like that, then to be able to access this or to take out this board, I needed to cut this a little bit ugly hole here, because this is the hole that I'm used for mounting, and I can't really move this in here because otherwise you can't access this due to the heatsink. But now I should be able to put in this plate. Look at that. So now it's not in the way. So far so good. Then I hold the different screws like that. Yeah, see? So now I can easily access everything, pull this out if I want to service stuff. So let's see the front with the new design. I sanded this a little bit and just gave it a little thin layer of spray. And then I think I should be able to assemble everything now. Oh yeah, and the display frame. Also again, a little bit of sanding and spray paint. This is not supposed to look like a brand new super sexy product. This is a prototype, so it's okay. You can see this is 3D printed, no problem. So now this front is ready to install. So this is the enable switch, and of course as you can hear, a multi-turn. I actually initially designed some 3D printed plastic fittings that go in here, grabs the PCB, and you put a little nut here and whatnot. But it's just, I can't bother to wait for all these 3D printed parts. I just wanted to have this ready and done. And of course there's a fucking helicopter. Shut up! Can't hear what I'm saying. But anyway, now the Arduino will just plug straight in here, and it's gonna work. So this is how I made the USB connector extension, so it will fit through the rear plate. I just soldered the wires pretending the connector was in here, so I didn't need to figure out what is what. As long as it's the same as if the connector was there, including the metal shield and everything. So yeah, I think this will work. Now I can just plug the Arduino directly back of the display, and then I should be able to power it up from the PC via Arduino just to see that it is up and running. I am of course not surprised to see that it works, but I think I put the frame a little bit too close here, so I will just move the pixels a little bit more to the right, then it will be fine. I didn't use the entire screen area, so that is perfectly fine. I'm quite happy about this. So I am ready, I'm done, and it actually works. Oh my god, there was a lot of soldering and a lot of try this and try that. So here is a little thing that I did. See, that is actually my emitter resistors. So this is the local feedback resistors, and that will be all the gate resistors. That is not that important right now, but the emitter resistors, they provide local feedback, so the current sharing is doing its job, and this is really good. It does really work. However, the curve of the IGBTs, it's actually a little bit different between the 8 of them. So when you crank up the current and it gets hot and cold and whatnot, the current sharing was not exactly perfect. So when I measured, so this is the wire that measures the current, and this is the wire that controls the current. See, it is the same point, obviously, right? But before this, I just had it in one of the emitters, and then I could see on my input here, the current was not exactly linear as the meter said, and it's because current is not shared equally over the entire range of currents because of the curve of the different IGBTs. I even did select them, but only at one point I selected the gate emitter point. So what I did here to avoid this problem, from all the emitters I have now added the voltages together using all those resistors here. So now I have a sum point that is the average of all currents, and this is now my regulating point and my measuring point. And now it doesn't really matter so much if the curve is a little bit different from the different devices, and as long as my average is whatever it is. And so now my error is really small in both the set point and the readout. What else can I show you guys? So I'm using an LM358, and I got some different diodes here for turning the output off. I will of course show this a little bit better on the schematic. And so I have a manual on-off switch that goes into one set of diodes, but also I'm using the other half of the op-amp. So I'm actually measuring the input voltage via this high voltage divider. That's actually 2.2 mega ohm resistors, 4 of those, and then some other resistors down here. And first the voltage goes into that extra op-amp, and that is now my enable for the current regulator. So if the voltage is too low on the input, the regulation goes automatic to off. Also, I'm measuring the temperature directly on the top of one of the IGBTs, and by doing this I am controlling a FET over here with this voltage, and here is actually a resistor to control the set point. So set the set point temperature. So this FET will now turn on the fan. So let's see how that works. If I turn on, so you can see I got 59 volts, and now I got 1 amp, so that is 60 watts. So I've adjusted the temperature set point just a little bit over ambient temperature. So as soon as this Igbt is just getting a little bit over ambient, it will start to run the fan. And of course, if it gets hotter and hotter, it will just give more and more power to the fan. And again, the trigger point of this FET is very, very steep. So you get a very aggressive regulation, and you can hear now it's going more and more berserk. And this is only 60 watt. And this is exactly what you want. You want this to start cooling down as soon as you start loading this. We've got a lot of air out here. Yeah. You can... See, this is 968, 69, whatever milliamps it is, right? Yeah. That's what it is. So of course it works. Yeah. Disable the current, and then after about a minute the fan will stop again. Completely automatic. Oh, we can even hear. Oh, it's that fast. Is that effective, this temperature regulator? Isn't that just nice? There's a little detail I need to explain that is important for the performance of loads like this. See here on the input, I got 2 red wires on the positive input. One of them goes to the common point where all the different Igbts gets their positive voltages from, but the other one is actually isolated. So this is my voltage measurement point. So there's no current going in this wire, and therefore there's no voltage drop over this wire, right? So that means I am actually measuring down there, right? And the same goes with the return. So I got 3 blue wires to the return. 2 of them goes to the common emitters on each of the 4 Igbts, but then the last one of the ground return wires goes to my little control board. So that means there's no current going in this return wire, no voltage drop over this wire, and then there's also no currents going around in this board as well, at least not in any magnitude at all, right? So that means there's no voltages over this board, and I will get a very reliable and stable current regulation. So of course this is not super important in a 1 amp load like this one, but of course you can copy this design to 10 amps or 100 amps or 1000 amps or whatever you like, and of course the more current you play with, this trick is more and more important, obviously, right? I just wanted to show exactly how to do it right. Another thing to talk about is stability. Because this is a feedback system with a lot of gain, of course it would love to be unstable. And also we got different timing constants in all the Igbts and all these resistors and whatnot. So one thing to start to play with is this integration capacitor. So of course you play with this 100 nano or 1 microfarad and in this area, and then you play with what is best. And when you're done playing with that, then there is another little capacitor we need to play with, and that is the input capacitor. Because of course you need to have a little bit of stability between the input. What if there's a long wire with inductance and whatnot in the source you want to load? So Look at that. This is about 300 kilohertz of instability, and I got only 100 nanofarad on the supply. So that is not enough. Let's see if I put in pling. See when it is connected. See, I'm just holding them in parallel, right? Then it's all gone, nice and stable. So you just need to find the magic point. And now my problem is I need 200 nanofarad in 1 kilovolt. Damn it, that's a quite big capacitor. Let's look a little bit on the schematic. So this is my fast hand-drawn schematic with all my notes and changes and upgrades and whatnot. This is the schematic. Let's look a little bit at the details. Here is the fan regulator, and this is a very simple system. As you can see, only one NTC at the set point and a random FET, and then your fan. So this system you can use for anything you want to temperature regulate or auto start your fan when something gets hot. Just glue the NTC directly on stuff that gets hot. This way you get the best regulation. For this product I am using a Max 6141 temperature stable reference. And it's of course because I want a very stable voltage here, so I can divide it down to the full scale of my ADC range of the Arduino. So this is about 1.1 volt. And I'm using about 1K pot meter here, so this is a 10 turn. Very good quality is of course needed. So and that is basically what there is to say about the set point. So the measurement is summed via the 10 ohm resistors from the local feedback resistors, the 9.1 ohm resistors, that's the local feedbacks, and this is the current path that goes through all the IGBTs and through the 9R1s and then back to the return. So the sum here goes through this resistor and to the feedback, and then the op amp controls all the IGBTs. Yeah, here is the resistor that I use to calibrate the readout. And for low leakage, when this thing is in active mode, I put in two 4148s. So I got really good low leakage. So this is the switch load enable. It is shown in enabled status, in enabled state. So there's no voltage here. And of course there's nothing to pull up the feedback. So of course if you pull up the feedback, this regulator op amp is going to pull down the output and this way turn off everything. And this is how you want to do this. You don't want to put in a mechanical switch or something in your ground or in your positive input, because it's high voltage. And also what happens if you do that, then this regulator is going to raise the voltage to maximum when it sees no feedback. And because there is the integrator time here, because you can see the problem, right? This will be high and you got time to response. So that means when you put in a signal, this regulator will have fully shorted, so the current will be insanely high, and this is not good when you come with 1,000 volts. It could be 1,000 amps or something. It will blow up everything here, right? So this is a bad idea to do it that way. So load switch enable here is a good way to do it. But on top of that, I have added an automatic turn on system for voltage feedback. See, I am measuring the input voltage. So I need to divide this down to a very low voltage, 0 to 1 volt for the Arduino. This is just for the display down here. So here is a higher voltage that goes to a comparator. So this op amp, the other half, is working as a compare. So it compares with a very low voltage, so 50 millivolts. So that means when the input voltage is between 7, 8, 9 volts, or something like that, it's really not that important. At least it is in that area. Then the output here goes low and enables everything. And when this is done this way, there will be a smooth current slope, like a current going on slope. So it's not a very, very fast or very ugly and nasty going on. So this is a very, very good way to do this. Definitely needed for high voltage stuff. So to make stuff simple, I just drawn 4 of the Igbts. Obviously I got 8 of them. You can scale this to any size you want, and of course you can use FETs, you can even use NPN transistors, you can use whatever you want. All you have to do is play a little bit with the resistors here as well, of course. And this is the final product, ready to be used.